class, I will go through very briefly about some of the problems for test 4 review, so that you can work on this problem for grade. So for the first one, it is saying that we have you have two setup. One is for water, one is for crude oil, and usually for pipe flow, viscous force is the dominant one here, so that's why you need to use the Reynolds number. So you can set this problem like this way: Reynolds number for model and Reynolds number for prototype. You can consider one of these as model, one of these as prototype, and then you can solve the unknown. Just make sure if you consider water as model, all the given values for water should be for model, and all the given values for the crude oil, that should be for prototype. Okay, for the second one, as I said in the class, this one is for the optimum performance of mixing blades in diameter to be tested using a model 1/4 of the size of the prototype. So that means model over prototype is actually like 1/4 this one, or you can say dm over dp, because I am seeing diameter here. Now one thing is, since it's a mixing blade and it's rotating, so it has the angular speed, but for any non-dimensional number we didn't see the angular speed, so you need to convert the angular speed into the linear speed. So linear speed v equals to wd over 2. So that is the linear and that is the angular. And now we need to think which number we need to use. Since it's water is in contact with this blade, so viscosity and viscous force, or the surface resistance, that is the prominent force here. So we need to use the Reynolds number again. So Vd over viscosity, and for this V you will use this relation. Okay, so that is for question number 2. Question number 3, the flow of excuse me, the flow of water around the structural support is something when the temperature is something. If it is studied using a model built to a scale of 1/12, and using water at a temperature, determine the velocity of the water used with that model. Again, though it's kind of, it seems it's it's open channel flow, it's not the pipe flow, but if you look at the question description, basically the dominant force is what is the friction along this surface. So that's why you need to use the Reynolds number again. So Reynolds number for model, Reynolds number for prototype. Okay, so and then you can solve this question. Let's go to the next question. Compute head loss due to the friction. That means you need to calculate the head loss, the major head loss for this one. For these two, what you need to do, since it's major head loss, you need to use the Darcy-Weisbach equation, v square over 2g. Now the only problem is everything is given. It's just you don't know the friction factor. Now for the friction factor, you know it's different for laminar and turbulent. Now the problem is, question is, how can you identify whether the flow is laminar or turbulent? So Reynolds number less than 2300, Reynolds number greater than 2300. Excuse me. So once you know this one, so you need to calculate the Reynolds number, and once you know that, friction factor will be 64 over Reynolds number, and for this one, friction factor you need to find from the Moody's diagram. Okay, so that's how you can solve this one. Question number 5. So for question number 5, it says that some diameter of pipe is delivering water from one reservoir to other reservoir. and you need to find the discharge, and you need to find the pump pump power. Okay, so for discharge, you already know this is a type 2 problem. Okay, and if you look at here, the velocity is not given. That means you can't find the discharge directly just by using the q equals to av. You need to find the velocity, and again, since it's type 2 problem, without the velocity you can't find the friction factor, and without the friction factor you can't find the velocity. So it's kind of like a problem where you need to solve for 2 parameters. So you know what you need to do. You need to do a little bit of trial and error. So at first you need to find the head loss, because the head loss is f L over d v square over 2g, and f this one. Okay, and we need to look for if there is any minor loss sources here. They didn't say anything like ignore the minor losses or something, so you need to consider the minor loss also. So your total loss will be head loss plus summation of KL v square over 2g. That is the loss. Now the magnitude of this head loss is directly not given, so what you will do, you can apply the energy equation between A and B. So if you do that, since there is no pump, no turbine, so if you do that, you will get something as head loss or HF. So you can directly use that to here. Okay, now once you have that, so HL equals to FLD v square over 2g summation of KL v square over 2g. So from this one you can express V in terms of something over F maybe. Okay, and for minor losses, basically you have this one and this one, which is the flush entrance, and this one is the discharge pipe. Okay, so KL is 0.5, KL is 1, so that's what you can get for summation of KL. So once you have that F, you know you need to do that table where you will assume F and finally F from Moody's diagram. Okay, and once you know the F, you need to find, you will get the Q, and for the part 2, power is gamma Q H. Let's without a change, determine the horsepower of the pump to be installed at an efficiency of 70%. Consider the entrance and exit losses and the water temperature of 10 degree. So to do this part, you need to find the pump head, and you can again just consider here there is a pump and apply the energy equation between A and B. So that will give you the head pump head. So this one is from A, and you can find the pump head by applying energy equation, and there is efficiency also, so you need to consider that part. By doing that, you can calculate the pump pump power. Okay, now this one is two reservoir connected by a long cast iron. You know the Q, you don't know the diameter, so that is actually a design problem or type 3 problems. So what you will do again, you will apply energy equation between 1 and 2. So that will give you something head loss value, and then you can set that head loss as f L d v square over 2g summation of kl v square over 2g. Now you need to find what are the minor sources you can get. So here minor sources are glow valve, 2 elbows, flush entrance, and the exit. So that will give you the KL, and you will have everything here except the F value. So what you will do, you will find the diameter or the equation for diameter in terms of function F. So most probably you will get an equation for this, not just the D, because you have some numbers here. So that's why you will do that. And once you have that, you can friction factor, Reynolds number, epsilon over D, and from Moody's diagram. Okay, so once you do that, you will find the diameter. Suppose you got something around maybe 7 or something, I don't know, 7 inches. If you look at this table, there is no commercially available 7 pipe, so you need to choose the 8. So the design diameter will be 8 inch. Okay, now for the next one, determine the power the pump must supply in order to discharge amount of water at B from 3-inch diameter hose. So you know the pipe material, surface roughness, and everything. So basically what you need to do, apply energy equation between B and A. So that will give you something pump head in terms of head loss and something. Okay, so F L over D v square over 2g something. Now you will see you don't know the F, so calculate Reynolds number if it's laminar, if it's turbulent you need to calculate the Moody's diagram. Okay, so Moody's diagram, you need to do the epsilon over D and Reynolds number. Okay, and for question number 8 and 9, as I said, these are for the dimensional analysis, and for N you will just write down all the parameters are given here, that will be your N. So for the first one, V, viscosity, density, and pressure, and from table 8.1 you can get the value LT. Suppose for P it's so for P it will be M, not P actually, for density it will be ML3. So you can get all of these and you will see that N equals to 4 and M equals to MLT. So that means you'll have 3. So number of pi terms will be N minus M, which is 3, and after that you can do the rest of the, you can look at the class examples for more details. The same thing for class example 9 also. So thank you class, please let me know if you have any question.